So hi everyone, today we finalized basically the second block. So it will be another dynamic model and in continuous time. And this model, it's not based on some particular paper, it's more like, some kind of comparatively old but quite influential type of literature. And this lecture will be just some aggregate of this literature. But at the same time, it will be, quite practical in the sense that it will be just one problem that we're gonna just solve. So, without all these, kind of introductory things, so how the problem looks like. So suppose you operate an oil well, that is, you are digging oil somewhere. And you already own this oil well, so it's yours, and suppose you didn't pay anything for that. And then in each moment in time, you have a decision to make, right? You either continue digging oil, so it's like costless, like, you do not have to pay anything to continue digging oil, right? Or you decide to shut down the oil well. But the thing is, when you decide to shut down the oil well, you cannot bring it back. That is, you cannot re-enter the market at some point in time afterwards. That is, you have an irreversible decision whether to stop digging oil, right? Your profit from digging oil is governed by the Brownian motion. That is, XT here is your current operation profit from digging oil. It can be positive, it can be negative, whatever, right? So we do not restrict it to any domain. And according to this Brownian motion, it evolves like that. That is, your profit in the next instant, right? Remember that in continuous time, we divide time in small increments of length dt, right? So your operation profit in the very next instant is almost the same as it was before, but plus some marginal changes. So the first is marginal change, which represents the drift, right? So, or trend, whatever, you can call it whatever you want. That is, you have some kind of, deterministic component of the evolution of your profit, right? For instance, oil constantly increases in terms of price, right? So, and there is a predictable trend around. So you can formalize it in adding these kind of constants, right? That is, you have a slope of A in terms of change of your profit. And the second component is some kind of random component, right? It's just some noise, that is some oscillation around the trend, right? In general, if you remember, that's exactly the form of any Brownian motion that we consider, right? In the mathematical lecture. That is, your value of this process in the very next instant is almost as it was before, plus some deterministic change and plus some random change. Here we assume that this drift is non-negative, right? So you have a positive deterministic component in terms of profit, and this random component dz, we assume it's normal with mean zero. That is, it oscillates around the trend, and the variance is dt. This is standard for any Brownian motion. All these assumptions, right? Except the fact that generally we do not necessarily assume that the drift is non-negative. Right? Here, for simplicity, we assume that it's non-negative. And in each moment in time, if you continue digging oil, you get exactly xt, right, as your instantaneous flow pair, right? And your goal in this problem is to maximize your operation point, right? That is, when you are at time t, you observe current level of xt, that is your current level of operation, and you know how it will evolve in future, right? It will evolve according to this process. And what you try to do, you try to maximize this discounted flow pair from digging oil. As you see here, right, as we discussed, XT is not necessarily positive, right? So with some bad draws from this random noise, right, you can get quite deep in negative area in terms of XT, right? And therefore, potentially with some kind of with negative instantaneous profits, you can decide to shut down. So it's not necessarily, kind of an obsolete decision, right? Intuitively, it's like if you go well today, right, you continue to operate. If you do not, if it doesn't get well today, right, you decide, right, between shutting it down or just continue operations. And your goal is kind of to optimally decide when to continue and when probably to exit the market. So here, as you see from this discussion, this problem is kind of an optimal stopping problem, right? Because we, from the start, assume that if you exit this market, this decision is irreversible. This significantly simplifies life, because if you do not assume irreversibility, that is, you kind of exit at bad times, right, and you get back in good times, this will get much more complicated as a dynamic problem. But here, it's like in any point in time, your game tree, if game tree concept is not very applicable for continuous time because you do not have next instance in continuous time. But basically, your game tree is more or less like in each moment in time, you decide either you go through the straight line of continuing operation, or at any point in time, you kind of can exit this market, right? And stop the game basically with a terminal payoff of zero. I mean, like terminal payoff of zero means that your profit from today onwards will be zero, but of course, already accumulated profit won't be neglected. It's already collected. So what is important about this form of profit is that it has inertia, right? Because if you have some XT today, right, tomorrow your profit won't be that different from your current profit. And that is quite natural because it's believed that the prices, for instance, in financial markets, they all follow Brownian motions, right? That is, for instance, with zero drift, right? So it's kind of your best prediction for tomorrow's price will be your today price, right? And some noise. What you can estimate is more or less like volatility, this like sigma, but otherwise you cannot predict. And therefore here, if we assume like roughly that you sell the same amount of oil in any point in time, then your profit is basically your sales times the price, and therefore your profit will be governed by the Brownian motion. So it's kind of a natural assumption how to model profit here. So it's not artificial at all. And as we discussed, what is important is that your profit doesn't change like, too much, right? So in the very next instant, it will be approximately the same as it was before, right? And therefore, you won't be too far from the point where you started in some kind of small amount of time. And therefore, it suggests how the optimal strategy looks like. Because if your current XT is quite large, right? So it's very positive. Then you have no reason to shut down the well, right? Because you already do pretty well, and you expect that in the future you will do pretty well as well. So why to shut it down at all? But when your current XT is very negative, right? Then potentially you can decide to stop the production, because again, because of this inertia, if you are very deep in negative numbers with your current profit, then it suggests that in some reasonable time horizon, you will still get negative payoffs, right? And therefore, if at all you will get some positive profits in the future, right? This future can be too distant from today, right? And because you discount future, even arbitrarily large profits in very distant future won't be able to compensate for current, liabilities, current, negative profit, right? So here we kind of see very large XT, you continue operation. Very negative XT, you potentially would decide to shut down the work. And if you go like, to XT being arbitrarily negative, right, then you clearly will want to shut down the work, right? And therefore, here I say it without proof, right, without formal proof. But this kind of logic suggests that optimal strategy in this problem is a threshold strategy. That is, there exists some X bar, right, such that above it, when your current profit is above it, you continue digging on. And when your current profit is below this X bar, you decide to exit the market. We do not know the value of this X bar, right? But what is important, we just here assume that your optimal strategy exactly takes this. And we will use it next. So our goal is basically to find this X bar because XT, we observe it in any point in time. And when we know X bar, we can fully characterize your optimal behavior, right? It's like just look at your current profit. If it's above, continue. If it's below, exit the market. That's it. And that's exactly what we're going to do. So again, it's quite similar to the problem that we analyzed in the previous lecture. So we again have like a binary choice in each moment in time, right? Either you shut down the well or you continue. When you decide to shut down the well, you exit with a terminal payoff of 0, right? Your future payoff is 0. And therefore, your value function from these choices is trivial, right? It's 0. So the value function, which represents the value of exiting today, is just a constant, which is equal to 0. And when you decide to continue operation, right, then you get instant profit, which is XT is your current operation profit, times DT, right? It's this small time increment. And then your continuation value, where your current XT evolves to XT plus DT. Therefore, the Bellman equation is given like that. So in any point in time, with your current XT, you choose between these two options. If you shut down the well, you get 0. If you continue, you get your current payoff. Then you discount by, a DT interval, right? And then in the next instant, you will move to the state variable, which is XT plus DXT, where, it's purely notational, where DXT is the change between the next value of X and your current value. So basically here, what is written is exactly X of T plus DT. But in this form, it's marginally better to write it here, more convenient. And after all, we take the maximum because, you have two options, and in any point in time, you choose the option which is superior, right? If 0 is larger than continuing operation, you exit and you get 0. If continuing operation is larger than 0, you continue operation. So it's like that. So let's move forward and actually solve this Bellman equation. So we already represented our optimal decision rule, right? So we already characterized that there exists some X bar such that if your current XT is lower than X bar, you stop operation, and therefore for this region, right, 0 is larger than continuing operation. That is, your value function is equal to 0 in this region. When it's vice versa, when your current XT exceeds X bar, right, you continue operation, And therefore, you can explicitly write that your current value function is equal to this expression, right? And again, as in the previous lecture, I mean, like this first case is trivial, right? You already know the value function there, but the Bellman equation for this region will result in a differential equation. And as before, the solution to it won't be unique, right? It will have some degrees of freedom. And remember that we also do not know this x bar. And eventually, after some additional considerations, as before, we will have two unknowns, like 1 degree of freedom from the differential equation and this x bar. And we will again impose already familiar conditions, which are value matching and smooth pasting, to glue two parts of the value function. This is the first part, which is for xt below x bar. And what we get here will be the second part. So that's the plan. Let's now go with it, and we'll do the second part here. That is, we will try to construct a differential equation for the value function in this region and actually solve it. So we assume now that you are in a region, oh, sorry, here it should be x bar. I will correct it in the slide. So you operate the web, and therefore you can explicitly write that in this region, we have the following Bellman equation, right? Now, as always, we need approximations, right? Up to the first order. So first is the discount rate, right? Here, it's the same approximation as always. Remember that everywhere you need approximations such that they give the first order approximations in terms of dt. Right? So here it's always this type of approximation because all other terms are of order dt squared, dt cubed, and so on. And according to our convention, dt squared is already 0, right? So we do not write it. Here, in case you operate with Brownian motion, right? Here is the value function where you have some argument plus some marginal change. Right? And here you can use again Taylor rule expression, but when you operate with the Brownian motion, when you approximate the value function, you always need to approximate here up to the second order. Why? Because this dxt, right, this one, if you look at the Brownian motion, actually it turns out that this dxt squared is proportional to dt, right? We already kind of roughly discussed that in the mathematical lecture, but it's just, you know, a convention for you. When you deal with the Brownian motion, when you use Taylor rule approximation for the value function, you need to go up to the second order. And that's the only case when you need to go in anything out to the second order. But don't worry, I mean, like in the midterms and everything, it will be explicitly written basically what you need to do and all these approximations. So you don't have to memorize it too much. So let us just know what we need. Or we know already like what to substitute here. And we have this approximation for the value function within this expectation. So the first thing that we need to do is just to take the expectation from this term, right? Expectation is linear, so we just add expectation to all the terms here. So eventually the expectation here is just this one. Remember that what you take expectation, right? With respect to what? Here you have xt. Xt is known to you in the current moment t, right? You observe it, it's your current a. dxt is not observable to you now, although it has time subscript of t, right? Basically, this term is like that, right? So it's your change from today to tomorrow, right? and you do not know it, right? So here, when you have all these expectations, it's basically what you expect in terms of change, right? So all the expectations are with respect to this dxt. So going back, we take expectation from this expression. So xt, as before, it's just a constant for you to take, right? So first you take expectation with respect to this, and it's just a constant for you. Here, when you take expectation, right? So again, this is just a constant, and here just expectation of dxt. Let us look at what dxt is. This is a Brownian motion, right? How your profits evolves. dxt is the same as we just, subtract xt from both parts. So here it will be dxt. And therefore, expectation of dxt is just expectation of the sum of these two terms. This is just a constant, right? A and dt, they are both just constants, right? dt is some kind of artificial constant, right? It's just some time increment which we play with, but in any case, it's just a constant for the expectation. And the randomness is purely here, but remember that dzt, it has expectations here. So expectation of dxt is just a times dt. So yeah, so here we just substitute a times dt. So here, again, when we take expectation, all that is just a constant, so it transfers directly here. And here is like the most interesting part is the expectation of dxt squared, right? We derived it actually in the mathematical lecture what it's equal to, but let us do it once again. Let us go to the definition again of this Brownian motion. So dxt, again, it's just the sum of these two terms. When we need to take expectation of square of some random variable, right? Remember that the variance of some random variable is equal to the expectation of the square minus the expectation of this random variable squared, right? There's some standard formula. And therefore, expectation of the square is equal to the sum of the variance of this random variable and the square of its expectation, right? So the variance of these two terms together, right, is equal to just sigma squared dt, right? Because this is a constant, it doesn't have any variance. So all the randomness is here. The variance of this dzt alone is dt, right, according to the definition. And sigma is just a constant multiplier. So in total, it's just sigma squared times dt. And the expectation of this, as we remember, is just a times dt. And when you square this expectation, it will be a squared dt squared, which is 0. Right? So eventually, it turns out that the expectation of the square of dxt is just sigma squared times dt. Right? We derived it. If you want some kind of more detailed, you can look at the mathematical aspect. What's here? So eventually, when we just need to calculate that, we just substitute sigma squared times dt. And that's almost it. So now we just need to substitute this approximation here and this approximation here. As you see, we used second order approximation for xt, right? And this resulted in just first order approximation for dt. All further terms would result in higher orders than dt, and therefore will be 0. So let us substitute both of them here. So this is an original equation, that is with two substituted approximations. Again, as you see here, it's just constant and proportional to dt, constant and terms proportional to dt. Again, you use the fact that when you multiply terms proportional to dt, you get zeros, right? So eventually, when you multiply all of them, that's exactly what you get. We already got rid of terms which are dt squared because they're zeros. All the time, just to check yourself, what you should get is that the value function in the left-hand side cancels out with some value function from the right-hand side, right? So you always should get a term which is exactly the same as in the left-hand side, and they cancel out. And all other terms have to be proportional to dt, right? So as you see, when we cancel out, we have dt around every other term. And then we just cancel this dt, right? And that's exactly what we get eventually. And then we transfer this term to the left-hand side, and that's the resulting differential equation. As you see, it's a second order differential equation here, right? And what is nice about it, it's linear, right? So, you don't have any complicated coefficients around unknown function, right? So here is just linear of xt. So here is constant, here it's total constant, all the constants. So it's quite a simple equation, actually. Then you will see the general solution to it. It won't be look that simple, but actually for the differential equation, it's simple. What is important about second order linear differential equation is that they have 2 degrees of freedom, right? That is, standardly, when you have like nth order differential equation of kind of normal adequate form, then the general solution to it has exactly n degrees of freedom. And that's exactly the case here. So it turns out that the general solution is given by this. So it's the sum of some linear function, right? So here it's linear function, plus 2 exponents, right? So here is just some constants which depend on all these parameters. So we have R, A, which is drift, and this sigma square, which is a variance, right? And all of them, they participate in these constants. But eventually, these are just constants. You do not guess them standardly. You just know more or less from theory in what form the solution to this equation should be. And then you just know that it's some kind of exponent from linear function. So it's basically e to the power of some constant time xt, right? And then you just substitute this form and then get a quadratic equation for this coefficient, basically, and just solve it. The result in some constant. So that's the general solution. Also, in the midterm, you shouldn't be afraid, right? I mean, with the guided instruction, you should be able to receive this differential equation, but you won't need to solve it, right? The explicit solution, like the explicit general solution, like this one, will be given to you, right? So you don't need to derive or somehow solve the differential equation. So that's the eventual answer. So as you see here, we have 2 degrees of freedom as promised. And also remember that we didn't know this x bar, this threshold, right? So in total, it seems like we have 3 unknowns, right? And I promise that we'll have just 2 equations, so not enough. But it turns out that in this particular problem, we need some additional considerations. So, and we'll actually begin with these additional considerations. So what we're going to do, we just actually will show that C2 has to be equal to 0. Why? Because we need kind of to impose some boundary conditions. It's called here. Suppose your current profit xt is very large, right? That is, your current profit is arbitrarily large, and then the probability that you will ever shut down your well is quite negligible, right? Or even if in some scenarios you will shut down your well, it will be in a very, very distant future, right? Which you discount a lot, right? And which value for you today is negligibly small. And therefore, what it means? It means that the value function, when your xt approaches plus infinity, right, when it becomes arbitrarily large, should be equal to just the value from operating this oil well forever, right? So with increase in xt arbitrarily high, your value from operating the well should approach the value from operating this oil well forever, right? Because the probability of shutting it down becomes arbitrarily small. And therefore, what it means, we need to basically calculate the value of operating the oil well forever without a possibility to shut it down, right? And therefore, this value is quite straightforward. We just integrate xt, your profit in all the points in time from today to plus infinity in time, right? So this plus infinity in time, it doesn't have anything with where xt is approaching. It's like you integrate from today to infinity in terms of time. This is just a discount rate, which is 1 today when you substitute t here instead of tau. It's 1, and then the higher tau is, like the more you discount it. And here you have exactly x tau, like your current profit, and you start with index t and afterward. Then we just substitute x tau as just a function of tau, right? What you know today in moment t, that on average, right, here is expectation. Because you cannot surely predict how xt will evolve, right? So you have to rely on expectations. So in expectation, your x tau will evolve as your current xt, right? Plus deterministic time increment, right? Because remember that in the Brownian motion, your xt changes deterministically and stochastically. Stochastically, it always changes, you know, on average 0, right? And deterministic change is just, you know, with the slope of a, it was a times dt. And therefore, if you use some prolonged time interval, right, from t to tau, your deterministic change will be a times tau minus t, right? So that's exactly the expectation of x tau, conditional that you are in time t and therefore know your current xt. And the discount rate stays the same, and that's basically it. So you just integrate it. As you see here, xt is just a constant for you today, right? And here is tau. So here is just an integral of exponent, right? So xt is a constant, and eventually it will be 1 divided by r. Here it's more complicated. Here you can, you know, take away a, and here it will be tau minus t as a term here, but here you can use this integration by parts again, which is standard, right? When you integrate a product between exponents and a linear function, and eventually it will be a, all these terms will be a divided by r squared. So eventually the answer will be like that. And it turns out that when xt approaches plus infinity, your value function should approach this value. When we take a look at the value function, we see that these terms are actually the same, right? And therefore, it means that when xt approaches plus infinity, the sum of these terms has to be 0, right? Let's take xt being equal to plus infinity and just substitute. So when xt is equal to plus infinity, this is a negative number, right? So it's a negative number in general, so it's minus infinity here. And with minus infinity, this term is 0, right? So this term is already 0 when xt approaches plus infinity. Here, actually, it turns out that this number is positive, right? Because the number here is larger than minus 8. And therefore, when xt approaches plus infinity, this whole term multiplied by xt, it approaches plus infinity as well, right? And therefore, to actually make it 0, right? Because this one is already 0, these are equal to each other, so we have that this is 0 when xt approaches plus infinity. And therefore, the only possibility for us to make it 0 is just to have c2 equal to 0, right? So these were some additional considerations that we used exactly for this problem. I won't say that these additional considerations are standard for dynamic problems, but sometimes you have to impose it. So now we know that C2 is equal to 0, and therefore our general value function is slightly simple, right? And we get back to our standard procedure. So we now know that we have two unknowns, right? C1, which still remains here as 1 degree of freedom from the Bellman equation, and also this threshold point x bar. And as before, we need two equations to pin these constants down. And again, these two conditions are the value matching and the smooth space. Remember that the value function in the region where you decide to stop digging ore is just 0, right? It's just a constant, which is 0. And therefore, your value exactly at the boundary, right, should be equal to exactly 0. It's just value matching. And also, because the derivative of 0 as a constant is 0 again, right? The derivative of the value function exactly at this x bar should be 0 as well. So in this particular case, the value matching and smooth spacing, they reduce to these equations. In general, here instead of zeros, you should have like the value of the value function at x bar from the left, right? And here is the derivative from the left. But in our case, they reduce to zeros. So in terms of analytical expressions, right, it reduces to these equations. So this is the value matching condition. Remember that our value function was like that, and we know now that C2 is equal to 0. So we have just these two terms, right? So exactly at x bar, this expression should be equal to 0. And also the derivative of the value function at x bar should be equal to 0 as well. How you take the derivative here, when you take the derivative, like without substituting x bar, here it will be just 1 divided by r. It's a linear function. And here it will be still C1, it's just a constant multiplier. And when you differentiate this, you just plug out this constant term, right? So here you have this term, right? And then the same exponent. Again, very standard procedure how to find x bar is to express monstrous expressions from the first equation. So here you can express this one as just minus 1 divided by r to this bracket, right? And substitute this whole expression here, right? And then it will be simpler because you eliminate the whole constant C1 and get the expression and also this exponent, right? And get an equation purely for x bar. So when you do this, the resulting equation will be like that. Then it's purely mechanical. So here you see it's constant, it's a constant, it's a constant. So, you know, it's a linear equation eventually, right? Straight after substitution. And then it's up to you how you solve it. But after all, it turns out that what you get is that x bar is equal to this sum expression of all the parameters of the model. So R is just the discount rate, and A and sigma is these parameters of the Broad. What is kind of interesting about that is the following. So clearly first, I mean, like we are basically done with solving the problem, right? Because again, we were not that interested in the value function itself, in these constants C1 and this value function. We were interested in our like what is optimal to do in any point in time. Like we observe current profit, like what we should do, exit the market or continue operations. And it turns out this is a threshold point. You look at your current XT and look here, compare it. If it's lower than this boundary, you exit. If it's above, you continue operations. What is also interesting to mention here is that suppose A is equal to 0. That is, remember that A is this deterministic brief term, right, in our Brownian notion. If A is equal to 0, then basically your profit tomorrow is your profit today plus some random change, which is symmetric, right? It's normal around your current profit, right? Therefore, on average, you will just oscillate around your current level of profit in the whole future. And if we substitute A equal to 0 here, here it will be 0, here it will be 0. So eventually we will get, some negative number here, right? Because from this term, right, it will be minus sigma squared divided by square root of 2r times sigma. So eventually it will be minus sigma divided by the square root of 2r. But in any case, I do not care about the particular expression. What is important, it will be negative, right? And this is a similar things to what we observed in the previous lecture, right? Here, your decision to exit the market is irreversible, right? You won't be able to get back to the market. And therefore, even with, negative current profit, you still hope for the best, basically, right? When you are basically indifferent between, perspective. I mean, like you have exactly current level of X bar, right? With some probability, the profit can go, can restore, can go back to positive numbers. With some probability, it can be even deeper, right? But if it goes deeper, you will be able, to terminate it and get zero pay, like, you're kind of insured against too low profits, right? And this gives you opportunity basically to still wait and to use this option, right? That your profits will restore in some point in time. Because if you stop operation, you won't be able to get back. And therefore you still continue operation now, even with current negative profits. Only if your current profits is substantially negative, you exit the market. Because the probability that it will restore, it's too small and it will be all in the distant future. So you do not like it. So that's basically it. So the bottom line for today is that irreversible investment is kind of, it's more like an operation research problem. In English terminology, you have this area in science, which is operation research, which studies just, some practical problems of economics in terms of math. And here, what is particular about it, it's an optimal stopping problem, right? One of many. And honestly, economics can solve only optimal stopping problems well, because if you have richer choices, right, not just a binary choice between exiting the game or continuing and then potentially exiting. When you have richer choice sets, it becomes easily non-tractable, then economics cannot do anything. And this one is an optimal stopping problem, which is tractable because of that. Another example of such problem. Because in these optimal stopping problems, you can always write a closed form expression for one option, right? Because remember, in exponential bandits in the previous lecture, we were always able to write the value function from switching to the safe option, to the safe arm. Here, we can always write the value from exiting the market, right? This is 0. So you always know the value function partially already. Also, you always have threshold strategies, right? Which simplifies life as well. And in the region where you continue, right, with playing the game, right? Continue with the risky option as it was in the previous lecture, or continue operating the well as it is today. You can write a Bellman equation, which you can then transform into differential equation and then solve it sometimes, right? I'm not saying that you can always solve the differential equation, but most of the time you can. And then it will have some degrees of freedom, which you then standardly pin down with value matching, smooth pasting, whatever, right? So it's a standard procedure. And what is kind of instructive about this model, probably the only instructive thing about this model is that because your decision here to shut down the well is irreversible, that is, you cannot just, not operating when you have bad times, right? You have to exit. Then you decide to actually operate even with negative current profit because you hope the market will restore. And if it's, if it doesn't restore, you can always terminate, right? And get zero, right? And therefore, it turns out that on average, when you have negative profit, you still prefer to operate the well. So that's it. In the next lecture, on the next Wednesday, we'll have a lecture, and then in a week from today, we'll have a midterm for this second part, which are basically dynamic models in discrete or continuous time. So that's it. Thank you, and see you in some time.
Thank you. Goodbye.